Okay. Last time we did an example where there were multiple objects in the system. We had the platform, we had the person, we had the pulley, and by looking at the individual objects in the system, and calling them each their own system, we were knowing something about the relationships between them. In that case, that was that the acceleration of the person and the acceleration of the platform were the same. We were able to uniquely solve for all of the forces and whatnot in the system. This approach of picking your favorite component in the setup and analyzing individual components can be very helpful. Though sometimes you have to be a little bit more careful regarding the geometry of what's going on when you want to figure out how things might be related to one another. So let's take the case of a massless pulley that has two masses, M1 and M2, and they're attached to a massless rope which is wrapped over the pulley, and they're just hanging down. This one's simple enough that you know what the answer should be. If M2 is bigger than M1, I expect M2 to accelerate downward while M1 accelerates upward, and vice versa if the masses are flipped. And if they're equal, I better get something like that their acceleration is 0. Let's define up as positive. I'm going to put my origin as well at y equals 0. If we wanted to analyze the system of 2 boxes plus rope, I could start by first doing, the first box. And on M1, looks like there's going to be a tension pulling up, there's gravity pulling down, and that's going to equal the mass of that box times its resulting acceleration. And then if I do the second box, looks like the same sort of thing. There's a tension pulling up, M2G, and then that's going to equal M2A2. Notice if I do the pulley in this case, which was the trick from before, that tells us something, but maybe not what we were looking for, because what the green is telling us is that there's the tension pulling down on both ends, but then there's also the force that's holding up the whole system, F rod, and since it's massless, that better equal 0. So this tells me that the rod better be exerting a force that's equal to 2 times the tension, whatever that is. But really, it was a new equation, but it also introduced a new unknown. So in terms of what we do and do not know, it looks like we don't know the tension, we don't know this acceleration, we don't know this acceleration. And so we only have 2 equations with 2 unknowns, the bottom 2. So this is not uniquely determining or allowing us to solve the problem. This was similar to the problem from before. We got around it before by being able to say that the accelerations were the same in that case. And you might think here that the accelerations are very much related to one another. If one box goes up, the other goes down, and you would anticipate that they probably should be equal and opposite. That's the case, but we should be able to mathematically show that. And again, we want to come up with general approaches for how we can solve these sorts of problems. So the third relationship comes from a constraint, a geometric constraint of the rope, namely the rope's length. The rope is not changing size, as there can be more on the left and more on the right side of the pulley, but as the boxes move around, the length of the rope is not changing. That is a geometric constraint on the system, because that means that you cannot have M1 and M2 at arbitrary locations relative to one another, because they have to have a rope that goes up, goes over the pulley, and then goes back down to the other mass. So the rope length L, I'll call this little l, is a constant. Let's use that to write down a third relationship that will tell us something about these accelerations. here is where we have to be careful, because I'm going to write this down in my vector coordinate system where signs can matter. Positives and negatives can matter at the end of the day. So if my coordinate system is the origin on the floor, then that means this is the distance. We won't use vectors, I'll just say y2. That's the position to the mass 2. This is the position to mass 1. And then the rope goes all the way up here, which I'll say is the position of the pulley, y sub p, y for the pulley. And then if I want to measure the length of the rope, I should measure this length. I should measure this length. And then if I want to also include the part that's wrapped around the pulley, I can include that too. So I can write down that the length of the rope is the length of that hanging side on the left, which looks like it's going to be y pulley minus y sub 1. That's the length that goes from the box to the pulley. The length that's on the right side, y pulley minus y sub 2. And then if I want to include the part that's around the pulley, I might say that it also goes halfway around a circle of radius r pulley. So this might be something like pi r pulley or something. Not 2 pi r, but just pi r, half the circle, if you want to include that. Now the left-hand side, L, is constant. Some of these things on the right-hand side are constants too. Right, this is a constant. This is a constant. The pulley is not moving around, so these are constants. Maybe the pulley was attached to other pulleys, and then one of the pulleys could move. Then maybe it's not a constant, but in this case it is. The pulley is not moving up or down. This can change and this can change, so they are not constants. Nice thing about constants is that when I take a derivative, they go away. So I could take the derivative of this entire expression with respect to time, and that would show me that the derivative of L is going to be 0. The length of the rope is not changing with time. And then I have to see, okay, y pulley is a constant, so its derivative is 0. And then it looks like it's going to be minus y1 dot. Pulley is 0 minus y2 dot. And then the rest are constants. So there is a relationship between, in this case it says y1 dot equals negative y2 dot. Tell me the velocity of one box, the other box is opposite in direction, but equal in magnitude in this case. And so similarly, y1 double dot, just take the derivative again, is negative y2 double dot. Or if I want to use acceleration instead of y double dot, it looks like it's saying that a1 equals negative a2 as a result. And indeed, the acceleration of one box is equal and opposite of the acceleration of the other box. This is great because this is my third equation. I now have 3 equations with 3 unknowns that I can, so I can solve for t, a1, and a2 uniquely. Yeah, I might write this first as say t minus m1g equals m1 a1. Then also I have t minus m2g equals, and I'll write as negative m2 a1. I'll factor in that geometric thing right away. Now I have 2 equations with 2 unknowns. There's a t in both, and it's positive for both, so I might do equation 1, and then I might subtract equation 2 from equation 1. So the t's cancel, it looks like I get negative m1g minus negative m2g, so plus m2g equals m1 a1 minus negative a2, or negative m2 a1. So this looks like it's saying that m2 minus m1 times g on the left-hand side equals m1 plus m2 times a on the right-hand side, or that a, in this case, is m2 minus m1 divided by m1 plus m2, all multiplied by g to make the units work. And then you can pick your favorite equation, plug in what we just solved for a sub 1, really this is a sub 1. A sub 2 then being negative that. plug those in and solve for t as well. But we can also ask ourselves, does this make any sense at all? Well, let's take the case where M2 is bigger than M1. I imagine then that the right box should move down and the left box should move up. Indeed, that's the case. And if you look at this expression, M2 minus M1 is then therefore going to be positive. So the acceleration of box 1 is positive. We said up was positive, M1 goes up, M2 is negative, that goes down. If M1 equals M2, notice you get 0, what you would expect. And if M2 is smaller than M1, A1 is negative, M1 goes down, A2 then goes up as a result. So here was I combined two systems and then a geometric constraint. In this case, the length of the rope. Something good to keep in mind when you have things that are constrained by ropes and whatnot. Let's keep thinking about multi-particle systems. What if you want, in all of these cases, we've been taking one object in the system. We've only been having one thing inside the dashed red box, that I've been drawing, or dashed blue box. What if you want to have multiple things in the box? Or particularly, this apple is really trillions upon trillions of particles, though I'm treating it as a single point particle. Maybe now I can actually say something about why that's been okay. So let's suppose you're pushing on a box with some force F to the right. And this box has mass 3m. The reason will become clear in a second. In this case, and I want to analyze the motion of the box and the frictionless surface. Well, I take my system. This seems to just be a single object. In the horizontal direction, there's F pushing to the right, and that's it. So then I expect that to be equal to 3m times the acceleration in the x direction. Or that the acceleration in the x direction is going to be F divided by 3m. Pretty straightforward. Now suppose, upon closer inspection, you look carefully at that box and realize actually it's two boxes that just happen to be next to one another. One that had mass 2m and one that had mass m. And you just realized this. And you want to redo the physics experiment and calculate the acceleration. Well, of course, there's no reason why the acceleration should change just because you realize actually it's two boxes that are next to one another versus one solid box like we just analyzed. So I expect if I were to analyze the two boxes together as a single system, I better get the same answer as when I just called it a single box on the left. We could also analyze each box individually. What's going on in this case? If I start with the left box, and again, all horizontal motion, so I'm not going to bother with right vectors, why not? We should be precise. So on the box that had the front box, there's the force from the hand pushing on it, but then there's also now a force on 2m from m, or on the left box from the right box. And that better equal then the mass of the left box 2m times a as a result. Similarly, if I then take, and again, I'm really just focusing on horizontal motion, even though I'm writing these as vectors. Of course, there's the table as well, but there's no horizontal component there. If I look at the single mass, the only thing touching it in the horizontal direction is the other box. So that it has force of on m from 2m. Newton's third law of pair, of course. And that equals m times a, in the horizontal direction at least. Maybe I'll just get rid of the vector so that we're not confusing the matter. All right. So the Newton third law pair, of course, then connects the two forces on M from 2M and on 2M from M. Then there's the force from the hand, which is a given, and then the masses and an acceleration, which notice I'm already saying they have the same acceleration, because again, it would be weird if they did not. Because if they didn't have the same acceleration, that might mean that they're merging together into one thing or they're separating, in which case these would not be the right equations to write down, because if they lose contact, no more force. Now, of course, I'm not sure what just happened. Of course, this implies then that this implies that F on 2M from M is then going to be negative M times A by Newton's third law. And so the top expression then becomes F minus F on M from 2M equals 2MA, or that is F minus MA equals 2MA, or that says F equals 3MA, or that A as a result is F divided by 3M. Again, as you expected to be the case, the overall acceleration of the two boxes together better be the same as when we just treated it as a single object. But really what went on is that there are different kinds of forces interacting on different parts, but the interaction forces by Newton's third law ended up kind of canceling out in the overall grand scheme of things. But if you analyze each individual part of the box, clearly they are meaningful. For example, this then allows us to write down that the force on M from 2M, which we said was M times A, but we just said that A is F divided by 3M, so this looks like that force is then F divided by 3. The force that's going on in between the two boxes, that force has a value of F divided by 3, F from the hand divided by 3. So it seems, when you look at this, is that on the left-hand side there was just a single object that had this total mass 3m, the overall acceleration. On the right-hand side there was that same amount of mass broken up into bits. But since there was no relative motion between the objects, and they all share therefore the same acceleration, we got the same answer on the right-hand side, only really, right, by analyzing all the individual interactions. But that is the same answer as on the left, where we really just cared about what's going on outside of the box. In this case, it's only the hand that's outside acting on the box. And then those interactions between the parts of the box did not matter overall in determining the overall acceleration of the system. So to commit that to words, right? Notice that keeping with the single object system, we get the same answer as when we break the system up. And when we break the system up, the only interactions that are going on between those different parts now are Newton's third law kind of interaction contact forces. So I might say that the interactions internal to the original system are all contact forces. Within the system. I could break this up even more, right? I could turn it into 3 boxes, each of them has mass m, or 6 boxes, each of them has mass m/2. Of course, then you're going to have many more of individual interactions within the original 3m box. But of course, the acceleration will always turn out to be exactly the same. They will all move with acceleration f divided by 3m. And then you can calculate the individual magnitudes of all those interaction forces, which will be different, for different components. But we could have said something about the entire bulk system as a whole without having to break it up into bits. Just like how I can say something about this apple as a whole without having to analyze every individual atom that make up this apple. If I treat the entire system as a whole and there's no relative motion going on within the apple, then I can get the same correct answer just by focusing on the forces that are acting on the system from externally to the system, knowing that all the additional interactions going on within the apple all are Newton third law pairs that are canceling each other out overall to determine the bulk motion of this thing. So this is kind of using Newton's second law on multi-particle systems, but in this case, under the assumption that there's no relative motion within the system, that it's a solid object, say. So I informally call this Newton's 2 1/4 law, because I've combined Newton's second law and third law. Why not 2 1/2? Well, it turns out I have another one that I call Newton's 2 1/2 law, but we'll come back to that when we do momentum. When there's no relative motion, between objects in a system, e.g. a solid, then you can apply Newton's second law to the multi-particle system as not just F equals ma, but I'm going to write this as F net external equals m tot times A, where m tot is the total mass. So add up the mass, integrate the mass if it's a distribution, whatever you have to do. Then this F net external are only forces originating from outside the system. And that deserves a highlight. It's a puny highlight. So it's a bigger highlight. So again, just how in these boxes above, I applied on the left-hand side, you could think of it, if I on the left-hand side knew that it was actually 2 boxes, I could draw a big box over, both boxes in this case. And since there's no relative motion going on in between them as these things move around, I can just treat them as one solid object and only consider the forces that are acting on the system from outside, in this case, the force from the hand. And of course, the force from the table, if we wanted to look at vertical motion and then gravity too. For gravity, again, you can use the total mass of the system multiplied by g, if you're doing this near the surface of the Earth, right? M total times g would then be the total gravitational force acting on the system. And it's applied technically at the center of mass of the system, but we're not quite there yet. And we don't need to worry about that yet. So this is great if you have multiple objects in the system and you don't want to individually analyze each little part. You of course could, just like we did at the end of last lecture. I could analyze and draw little boxes around every particle in this apple. I would of course get the same answer after a long, arduous case of keeping track of Newton's third law pairs. Let me do an example that's kind of similar to one we did before that demonstrates this. Suppose there's a platform of mass m that you are standing on again. And there is a rope that is attached to the platform that goes up to a pulley. It goes over to another pulley. And then the rope comes down and you're holding on to the rope. These pulleys, I guess, have to be attached to the roofing somehow. And then you have mass little m. This is called like a painter's chair, I think it's called, or something like that. Or there's another word for it. Boson chair, maybe. Where you can pull down on the rope and you and the platform will move up. And the question is, how much force do you need to pull down on the rope to rise up at a constant speed? All right. So moving up at a constant speed, right, you and the platform are moving together. So you could do this by analyzing the platform as one system, you as another system, maybe your hand as it touches the rope as another system to establish tension, maybe one of the pulleys as a system. We could also get away with, since I and the platform are moving together as one solid, in a sense, unit, let me call my system me plus platform. In that case, I can ask myself, really I should have included my hand where we touched the... In this case, what forces, and again, this is all vertical, and let's let up be positive. What forces are acting on this system of platform plus me? Well, there's gravity, and it's pointing down, so I'm going to write that as big M plus little m times g with a negative sign. It looks like it is touching the rope here and here. I might say also here, so that there's 3 places where it touches the rope. If you imagine, I should have got a rope. Use this cord. But you can imagine if I'm pulling this down and this is taut, the part that's dangling kind of below, which is this terrible example because it's caught on something, where there's tension in this top part, but there's not really any tension in this bottom part if it's just dangling and it's massless. So that third one is not contributing any force because it's slack, at that part. But there is tension in the 2 on the top. And it's the same rope, though it goes over some pulleys. So I imagine that there's going to be 2T from the tension in that rope pulling up on the system, me plus platform. And is there anything else touching my kind of red blob I drew? No. So then this better equal the total mass times our resulting acceleration. But if I'm moving up at a constant speed, that's just saying that there is no acceleration. I could have also said that we're remaining stationary, but again, we can't think v equals 0 means force equals 0. I could be rising up at a constant speed. I'll have to exert the same amount of force as if I was trying to rise up or just hold myself stationary. Then what else is there? So there's a tension. So essentially, I guess we're done because we can then get the tension that you need. It looks like in this case then that the tension is going to be 1/2 the sum of the masses times g. And then if we want to be exact, right, I could take the system of a little tiny piece of rope just as it touches my hand. And that is essentially all that is saying is that if I'm pulling, there's a tension, pulling on that little piece of rope and the force that I'm pulling down from my hand, and it's massless, so that better equal 0. Again, just saying that the force from my hand is what's establishing the tension. So that what force do I need to pull down on? 1/2 the sum of the masses times g. From an engineering standpoint, this is actually helpful because notice that the force you have to exert is not the weight, m times g, of you plus the platform, but only half. You only have to pull down with half the weight. So, for someone who's 150 pounds, right, if I were to just hold them over my head, I would have to hold up the entire 150 pounds. If I had them, with some pulleys, right, I could pull down on a rope and lift them up, and I might only have to pull down with 75 pounds worth of force, for example, to lift them up at a constant speed. You can imagine you can put more pulleys and you can get mechanical advantage that way. One more. Suppose there's between two walls you hang a banner. And this banner has some mass, some total mass m. And it's uniformly distributed through the banner, so it's not weighted awkwardly on any one side. So, and you measure that the angle that the banner kind of makes at the edge, at where it attaches to the wall, kind of hangs, and it makes an angle theta at the edges. And of course that angle, if will change. And by symmetry, it must there kind of become perfectly horizontal right in the dead center, and then it angles back up on the sides. So it's uniform mass. So it's trillions and trillions of particles, but they're uniformly distributed. My question is, what is the tension in the banner at the endpoints? What is the tension in the banner in the middle? You might think with a distribution of mass, this seems like it's becoming a calculus problem. And if you want to pick an arbitrary location on the banner and figure out the tension there, it is a calculus problem. It's a more challenging problem because you have to figure out exactly the shape that it's hanging in, which I haven't really stated. I just know that if it's uniform and it's hanging at two ends of the wall at the same height off the ground, then by symmetry, right, I know that the angle it makes at the edges are going to be identical on both sides, and it's going to be perfectly horizontal right at the center. All right. Well, again, this all amounts to, if we can be clever about how we pick our system, we might be able to restrict ourselves to only forces that are acting on the system that we know how to write down, and then could easily solve for. So for example, at the endpoints, how do I figure out the endpoints? Well, I could start by saying my entire system is the entire banner, and call that my system. In that case, what's the force analysis? Well, the entire banner has mass of big M, so there's big mg for gravity pulling down on the banner in the vertical direction. And it's not moving, so that gravitational force better be balanced by some upward force that's holding the banner up. And if I look at my system, what's touching the banner in this case? Just the two endpoints at the wall where the banner comes in contact with the wall. So whatever the tension is at the knot, that's holding it up to the wall, actually no, I can't. I almost said that the tension is uniform throughout. That can't be true because I'm not treating it like a massless rope in this case. The tension does change. Again, I'm asking you to solve for the endpoints and the middle point. So I almost slipped up. But at least I know by symmetry the tension at the left endpoint and the right endpoint are identical. And it's at an angle. If I just look at the left side, right, here's the wall, then the banner kind of comes up here where it attaches to the wall. So wall on banner is going to be exerting some sort of force that's going to be pointing in that direction. And we said that this angle here was theta. So this is kind of force on banner from wall, which then is being balanced by the tension, or the vertical component of the tension, at the endpoints. So if I figure out the force of the banner on banner from wall, that is the tension at the end. So by geometry, it looks like there's the system where there's two walls touching my system. Looks like it's going to be 2 times the tension at the end, but it's the vertical component. So by the way that I've defined that angle, it looks like it's the cosine component. All right, take the dot product of this general vector with y hat. And then that better equal, in this case, if nothing's moving, so it's not accelerating, 0 in the vertical direction. And look, you can actually then solve that the tension at the end is going to be, then it looks like m over 2g, 1 over cosine, or secant of whatever this angle is. Now what about the midpoint? Well, again, let's be clever. I want the tension at the middle to be included, so that might suggest that I include the middle as part of my system. We just went through all this work of figuring out the tension at the end, so then maybe I make this my system. Where for the blue, there's half the mass on the right-hand side being pulled down by gravity. Do we want to do that? Actually, no, we don't want to do that. What I said is true, but that's in the vertical direction. Maybe we'll look in the horizontal direction for this blue system. Why horizontal? Because the tension in the middle of the banner is only horizontal by the symmetry of the situation. It becomes horizontal right in the middle. So there is a tension pulling the banner to the left in the very middle. So I'll say that negative T mid at this point. And then there is a horizontal component of the tension at the end, but only one for this particular system. So then this to me looks like then it's plus T end times, not cosine in this case, but sine of the angle. And that better equal 0, because there's no acceleration as a result. So then this looks like the tension in the middle is going to be T at the end times sine of the angle. But then we figured out that TE before was m over 2 g 1 over cosine. And that's all being multiplied by sine. Sine divided by cosine is tangent, so this looks like it's m over 2 g tangent of whatever that angle is. So even in these kind of distributed cases, we still were able to say something about tension at particular points, as long as we are clever about the system we choose. And one I will not solve right now, but I'll leave it to you. I remember this one very clearly because it was on my physics GRE. I think I got it right. I suppose there's a big box M with 2 little masses, little m and little m. Everything is frictionless. The 2 masses, little m's, are attached via a rope, in which the pulley kind of drapes over. And you push only on the big box with a force F. What force do you need to push on the big box with, such that the little boxes do not move relative to the big box, so they don't slide along, vertically or horizontally in any way as you push the entire system to the right? So the clue is that I'm asking about the case where there's no relative motion as a result of you pushing on the big box. And again, everything's frictionless. You can try it, figure out that answer for yourself. Let me just quickly, again, just to make sure it's clear of what I mean. these examples that we're doing in this kind of what I'm calling Newton's 2 1/4 law, right, does require that whatever system you draw, that there's no relative motion going on within that system. Now you might ask, can we go even more general? Where I could have, say, I want to have the entire solar system as my system. That is the sun and the earth and the moon and Jupiter and all of its moons and Saturn and all of its ring particles and lots and lots of different objects within that big system. And they're all moving, together as well as the solar system goes around the center of the Milky Way. But then they're also moving relative to one another as things orbit and whatnot. And absolutely, we can say something about, we can even draw systems where there's even stuff going on inside the system and say something about what overall the system is doing. That is what I call Newton's 2 1/2 law, or 2.5 law, and is essentially a statement on momentum. So that is why I'm holding off on introducing that until we do momentum. But that is kind of the most general way to write down Newton's second law, where you can use a system that is, a single particle, a bunch of particles that are rigid together, or even things that are internal to the system are moving around, and still get correct answers as to how the system as a whole evolves.